Recording. All right. So we talked last week about fusion, fission, actually, I guess, and nuclear reactors. Gave you an idea of how nuclear reactors work. Don't remember if I said last week or not, but I think it's really, it's kind of fascinating to me that our first engines were steam engines. We learned how to, like in a train, get a big steel pot of water, put a big fire underneath it, make the water boil. As the water boiled, the steam pressure built up, and we were able to guide that through pistons to push pistons back and forth with steam pressure. So our first power was steam power. Now our most advanced power, nuclear power, is steam power, just by boiling water. I mean, fuel is nuclear, but we're still just boiling water. Well, for today, I want to talk about nuclear fusion, and then I'm going to change the plans that I sent out on Sunday night for the upcoming week. But I'll save that till the end in case anybody else shows up to hear it. Now let's see. So I need pen. All right, so nuclear fusion. We talked about nuclear fission, which is the splitting of very large atoms. Now nuclear fusion, which is combining of smaller atoms. And at the basic, most simplest level, at the basic, most simple level, nuclear fusion would be combining two hydrogens to make a helium. This is the fuel for suns, stars, if you will, including our sun, which of course is a star. It is, in a sense, the, if you will, holy grail of power source. It's what many people around the world are spending an enormous amount of money to try and make happen. If we could harness nuclear fusion, and maybe someday we will, but it's still a little bit out there. If we could harness nuclear fusion, we could basically solve all of the pollution and energy problems of the Earth, because we could run nuclear fusion on hydrogen. There is an enormous amount of water on the Earth, and the water is 2 parts hydrogen for every 1 part oxygen, easily split apart. The products of nuclear fusion are not highly radioactive like nuclear fission. So we would make pretty safe products, release huge amounts of energy for a small amount of fuel, and almost no pollution. The pollution in nuclear fusion would come from building the fusion devices. I mean, if we could figure out a way to control nuclear fusion, once we got it, miniaturized, you could buy your box when you built a house, or even if you already had a house, you could buy your box, plant the box someplace in the ground around the house, I suppose, or leave it on top of the ground. And the hydrogen fuel would go in, the nuclear fusion process would start, and that would be that. You just keep getting energy out of this box for however long you had fuel in it. Super cheap fuel, hydrogen. But we haven't got there yet. So the only, we've done a tiny amount of nuclear fusion, but it's totally impractical for any, what should I say, any mainstream or even close to mainstream use. The only thing we've really been able to do with fusion is nuclear bombs. There's two kinds of nuclear bombs. There's fission bombs and fusion bombs. And so when you hear someone talking about a thermonuclear reaction, they're talking about fusion. And we've been able to do it uncontrolled, as in bombs. We haven't been able to do it in a controlled fashion, as in power plants. We wish we could. We're working on it. Why not? Known fusion requires a temperature of 20 million Kelvin. Enormous temperatures. No known material, at least at the time I wrote these notes, can withstand temperatures of even 5,000 Kelvin, and we would have to go magnitudes of order higher than 5,000 Kelvin. So this creates a problem for us. We've tried plasma containment methods, and we've got a little bit of fusion out of that. But the energy produced by the fusion that we got is only a tiny portion of the energy required to create and maintain the plasma. So if it takes more energy to make your plasma container, it's not really a container because it's not solid. But if it takes more energy to make your plasma containment than it does to actually get the fusion out, then what's the point? Well, the point is to try and find a way at this point in time. Inertial confinement has been tried without any kind of success. There is one other method, one other thing that the U.S. government is doing in a laboratory. Now let's see. All right, so the United States government, at a cost of something like $5 million, built this thing that they call the National Ignition Facility in California, Livermore, California. Now, this is an old article. This article is from 2012. It is huge. It's somewhere in the size of a football field. If we take a look at this picture right here, we'll get this picture. Let's see. So let's view the image, and then we can enlarge it. And so to give you an idea of how big this is, here you have a person who could, not standing up, but who could fit inside each of these little cavities if he were to curl up, for a nice cozy nap. So this thing is enormous. So that was 2012. And in 2012, people were like, oh, we're wasting all this money. This is just a big boondoggle, if you've heard that term. And this is pointless. This is just pouring taxpayer money down the drain. And maybe it is. So here's an article from 2014, 2 years later. Now let's take a look at this picture, then we'll look at the article, but let's take a look at the picture to give you an idea what's going on. So view image, and then enlarge the image. So obviously here's a person in a crane, and here are those big old cavities, pockets that we were looking at in the last picture, and you see that this basically just goes around in a big circle. And then right here is where the reaction is supposed to take place. So we've got this big arm sticking out with this little tiny reaction capsule at the end. A human, again, gives you an idea of the scale. Now, one more picture before we look at the details of the article. So this is the reaction chamber. Inside here is where the reaction, this is on the end of that little, looked like a pencil tip that sat out at the end of that rod where the guy was going up in the last picture with his lift. Now, so here's our reaction chamber. Let's try and give you some concept of the reaction chamber. Inside a capsule, the width of a number 2 pencil. Now, a number 2 pencil is just a regular old wooden pencil that you write with. So this thing right here is the width of a number 2 pencil, a regular old wooden pencil. From here to here is as wide as a pencil. And this little ball in the center is the hydrogen fuel. So basically lasers will shoot at this. Now let's take a look at some of the details. Because scientists say that they have actually got fusion to happen in that container as of 2014. So Lawrence Livermore National Laboratories, National Ignition Facility, consists of 192 beams. That's laser beams that make up the length of 3 football fields. So there, 3 football fields. So we've got these 192 beams of laser that focus on this one little tiny capsule smaller than the width of a number 2 pencil. Look at this. For a brief moment, the beams can focus 500 trillion watts of power. Now, 500 trillion watts of power is more, look what it says, more power than is being used in that same time across the United States, across the whole United States. So for just a, I don't know, few seconds, several seconds, they're focusing more power than the whole rest of the United States is using. That's a lot of power. The goal is fusion, the process where hydrogen atoms are squeezed together to make helium. When it happens, a lot of energy comes out. It could mean the answer to the world's energy problems, but fusion is really, really hard to do, as I've already expressed. So over the past few years, they've gotten a big fat F because they didn't do anything. They were failing. They figured out how to make it work. They got it to work. The new technique still couldn't reach ignition, which is the point where hydrogen fusion feeds on itself. In other words, where it starts going and keeps going on its own. They were only able to make a few hydrogens fuse while the lasers were focused, but that's a step. Ultimately, the goal would be to get it started and keep it going on its own. And then once we could do that, we would be able to harness the whole thing, hopefully, into a smaller package. Probably we'd start out with huge fusion plants and run through existing transmission lines like we do with regular electricity now. And then after that, maybe at some point in the future, we could get our own personal devices. So that's the things they've been doing with fusion. And that brings us, as you may have noticed, to the end of the notes for this unit. So I had originally said that we would be having, oh, by the way, any questions on this before we move on? All right, then. I had originally said that we would be having online class Wednesday and Thursday, tomorrow and the next day, with quizzes. I had forgotten how far along we were in the notes, so I'm going to modify that plan, and I will be giving you another worksheet tomorrow, and then another worksheet on Thursday, and then next week, and I still haven't figured out exactly how to do this online yet, but next week we will be finishing up the unit. The next unit that comes, I'm sorry, next week we'll be finishing up the unit with a test, maybe a death quiz, maybe another worksheet. I'm not exactly clear on that, and I'm not exactly clear how I'm going to give a test yet, but I've got, several days to work on that. After we're done with that test, the last unit will be the electronics unit. The electronics unit will involve building devices with kits and what they call breadboards, where you can just insert wires and don't have to solder them. Alex will probably be done in 20 minutes, and some of you may take a little longer than that. I'm going to have to probably get new kits ordered to make sure that all the parts work, because no one will be there to help you if the parts are defective. And the parts do go bad, especially when people are not careful with them. So we'll have to figure out how all that's going to work. I think I'm going to buy new kits and then either mail them to you or have you pick them up at the high school. I'm not sure what. Anyway, that will end the notes for this unit, and it will end everything that I have for you for now. Anything else before I sign you off? Well, all right then. You folks have a good day, and make sure there is a quiz out there for you now. Make sure you get that taken by 3 o'clock, and we'll talk to you later. See ya.